Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 87. It's on Kirchoff's loop rule, which is a powerful tool to look at circuits. And when combined with Kirchoff's junction rule, which we'll get to in a few videos, it really makes analysis of complex circuits possible. And so the way it's written is the sum of all the voltages in a loop is equal to 0. And so if we were to write that out, V4, so that'd be the voltage of the battery, minus V1 minus V2 minus V3 is equal to 0. So the sum of all the voltages is equal to 0. Now, how does that work? Well, remember the battery is a voltage lift. It's giving charge potential energy, and then we're losing that energy through this resistor, and that resistor. And so the sum of all of the voltage differences is 0. The lift minus the drop minus the drop minus the drop is equal to 0. Now, conceptually, a better way to think of that is like a roller coaster. When you're on a roller coaster, when you start, there's going to be a lift. So that's going to lift you up to the top of the roller coaster. Now the cars have potential energy, which is converted into kinetic energy. And if they play it right, you're going to get right back to the beginning again with no energy left. And so Kirchoff's loop rule is really just the conservation of energy in a loop or in a simple circuit. So the voltage or potential difference around that whole loop is going to be equal to 0. So we could look at, for example, a battery and a resistor in a simple loop. The voltage lift plus the voltage drop is going to sum to 0. Now, how do you figure out the voltage of a resistor? Remember, we simply use Ohm's law. And that's all you have to know about Kirchoff's loop rule in Physics 1. In Physics 2, we're going to add capacitors and then also parallel circuits to it. And so if we think back to that roller coaster, as we store energy in this sphere, it's just like storing energy in the charge across a battery. And when we let it go, we can lose some of that energy. We could gain some back. We could have another battery. We could lose some, gain some, lose some. And so you can have a really complex circuit, and we can solve it using Kirchoff's loop rule. So think of it more like this. So we've got a battery, which is like the lift in a circuit. It's giving those charge energy or potential difference, and then they're losing that energy. They come back to the battery again and they're gaining charge. This is a pretty simple model. Charge is going to be distributed through this whole thing, but it's a good way to think of what voltage is. And that's why we can't just measure the voltage through something. It has to be across something. For example, across a battery or across a light bulb. And so voltage is equal to the work done by the charge as they move. And so if we were to move, for example, 1 coulomb of charge, we could do 1 joule of work. That's what a volt is. And so let's make that usable. Let's not just short out our battery. If we put a light bulb here, as that charge moves through it, if it's a 1.5 volt battery, we're going to be able to generate 1.5 joules of heat and light coming out of that light bulb. And so if we look at a circuit like this, Kirchoff's loop rule lots of time is written like this. The summation of the voltages is equal to 0. So the first thing you have to figure out is which way is the current flowing, and then just basically current we'll say is flowing from the positive to the negative. So you can think about going through this loop in a clockwise fashion. To use Kirchoff's loop rule, you have to start at some point and be able to return to that same point by tracing out the circuit. And so we're going to say the sum of our voltages is equal to 0. So we'd write it out like this. We're going to start with a battery. The battery, since it's a lift, we're going to give that a positive value. So positive V1 minus V2 minus V3, because we're losing that potential difference in each of these resistors here, is equal to 0. And so we could solve for V1. V1 is equal to V2 plus V3. So let's do a simple problem. Let's say we have a 9 volt battery. We have a 10 ohm and a 5 ohm resistor right here. And then we've got a current going in that direction like that. So first thing we have to figure out is, well, what's the current going to be in this circuit? So we've learned earlier that we could just add these two resistances together. So that's going to be a 15 ohm resistance on this series circuit. So we're going to put 15 ohms right here. What's our voltage? That's given as 9 volts. And so we could solve for the current. It's going to be 0.6 amps. So now we just go around and we can use Kirchoff's loop rule. So if we look at this resistor right here, what's its voltage going to be? Well, we just use Ohm's law again. We know the resistance is 10. We know that the current is 0.6, and so it's going to have a voltage of 6 volts. What's the other one going to be? It's going to be 3 volts. And so you can see that the addition of this 9 volts minus 6 volts minus 3 volts is equal to 0. And so to think about that, and this model really works for me, think of that same circuit drawn like a roller coaster. So we could say the battery is right here. And so how much potential difference do we have, or potential do we have at the beginning? 0 volts, but we're lifting it to 9 volts as we go through the battery. We're giving it potential energy. That charge has potential energy. As it moves through the wire, that 9 volts is not going to change throughout here until we get our next resistor. And so this is a 10 ohm resistor. If it starts at 9 volts, what's it going to be as it gets to the bottom of that? It's going to be 3 volts. So we're going to have a voltage drop of 6 volts. And then that goes to 3 volts and back down to 0 volts on the second resistor that's going to be inside. Now if we do a simulation of that, this is a PHET simulation. I've got that same circuit drawn. So it's going to be 9 volt potential difference across it. We could look at the amps, and that's going to be 0.6 amps. Again, we just added those resistance, and it's going to be the same, current through every part of that circuit. And then the next thing we can do is just verify that those voltages are correct. So if we look across the first one, it's going to be 6 volts across that first resistor. And then if we were to look across the second resistor, using our voltmeter, again, we have to check it across that element. It's going to be 3 volts right here. But what would happen if we now make it a parallel circuit? So if we're going to build a parallel circuit on the other side, and let's just put a 10 ohm resistor over there. So if you think back to that roller coaster analogy again, what's going to happen as we move through that other circuit? Well, we had potential energy right here. We have 9 volts of potential energy here. We're going to have 0 volts of potential energy when we get back to here. And so what's going to be the voltage drop across that? It better be 9 voltage drop, 9 volts of voltage potential difference, and it's going to be a 0.9 amps. And so we could check that using our ammeter and then using our voltmeter. So we get a 9 voltage drop across there. Now, as you move into physics 2, you have to understand what's going on with not only resistors, but capacitors. And capacitors, remember, will store charge along plates. And so now we've got a simple circuit. I've drawn the electrons moving in the circuit, or in this time. And so we've got a 0.9 amps. So we've got movement right there. If we were to move across this one resistor, the voltage drop is going to be 9 volts. But now what I'm going to do is I'm going to add a capacitor. So we're going to split the junction right here, and we're going to put a capacitor right here. And watch what happens to the charge. The charge eventually stops. And so let me discharge that capacitor, and so it stops. And so we could even look at what's happening to the current. You can see the current is dropping to 0. So there is no flow. But now throughout the whole circuit, there's no flow. But now let's start to look at the voltage. And so with the resistors, we would expect across this one to be that whole 9 voltage, but it's not, it's 0 volts. And so where's the potential difference? It's going to be across the capacitor itself. And so when you're using Kirchoff's loop rule with capacitors, you can think of a capacitor just like a battery. That's where the voltage is going to be. Now let's put 2 capacitors that are going to be in series. And so if we look at the voltage across each of those, since they're the same capacitance, it's going to be 4.5 volts on each one. But if we change the capacitance of that next capacitor, so let's give this higher capacitance, so it's a larger capacitance, I moved it up to 0.20 farads. So now we find the voltage on the bottom part is 3 volts on the bottom capacitor. On the top one, it's going to be 6 volts. So that's that inverse relationship when we're looking at capacitors. And that's because we're storing that charge along that plane. And so did you learn to construct or interpret a graph of energy changes? Again, think of it like a roller coaster. Could you apply the conservation of energy that shows how the Kirchoff's loop rule works? And so again, it's the voltage lift is equal to the sum of all the voltage drops. Could you apply this to solve a simple problem? Could you then start to study capacitors? And we call those steady state circuits. What does steady state mean? Well, when you just hook it up, it's going to be transient. So we see a little bit of charge still moving, but eventually it becomes a steady state. And so understanding how a capacitor works inside a circuit like that. And then could you tie this to the potential energy, the ability of that charge to do work? I hope so, and I hope that was helpful.